Thank you, Ian. And good morning to all of our participants. Dr. Alexander Hegedus received a BS degree in mathematics and computer science from Alma College in 2014, and his master's in 2016 and PhD in 2019 degrees in atmospheric, oceanic, and space sciences and scientific computing from the University of Michigan. In the summers of 2016 and 2017, he interned at Jet Propulsion Laboratory. After receiving his PhD, he was assistant research scientist in the Climate and Space Sciences and Engineering Department at the University of Michigan. This fall, he begins a new job as a research engineer at Stanford Research Institute in Ann Arbor. I first learned of Alex and his work in conversations with my friend and his grandfather, John Kleinhexel, a HASP member. I'm very pleased this has led to this 3-session HASP class in which we can all learn more about our world and our nearest star. I want to make sure that all participants know that you can put questions into the chat box at the bottom of your screen at any time, and Alex will be happy to address your questions. Please help me give a warm Zoom HASP welcome to Alex Hegedus.
All right, well, thank you very much, Gordon, for that very nice introduction. As he said, my name is Alex Hegedus, and the title of my seminar series here is What's New Under the Sun? Part 1, Future and History of the Sun. And so you're seeing a lot going on in this title slide, and I'll be touching on each of these elements throughout the weeks. But to give you a little bit of a spoiler, we're going to be talking a lot about the sun, as well as radio waves that it emits. And we're also going to be touching on radio waves from space in general. So you see a lot of sources and ways of observing those sources throughout this title slide that we'll be touching on. And so Gordon kind of went through my most recent CV resume, so I won't repeat it, but I will take this slide to talk about how I got my PhD in 2019 in space sciences and scientific computing. Our department also has an atmospheric and oceanic, which is now like the climate half of the department. But I was more on the space side. And I got a dual PhD in scientific computing as well. And I think my work is really interesting because it's at the intersection of science and engineering. We have to keep up to date in the field to understand what the state of our collective knowledge and understanding is. And then when we understand the limits of that knowledge, we get to dream up ways to get data that could resolve these open questions. And so my work is in designing great big experiments that NASA likes to call missions, and building data processing and analysis pipelines to produce that scientific data to answer the open questions. And so this involves a range of activities, predicting computer simulations, and making mock-up data analyses and arguments to convince the people, the community, that the work is worth doing. And so that, all these distributed reviewers and the scientific community decides that it should go ahead and get funded. That's one thing that's kind of different, because with NASA missions in particular, the budget of these is pretty astronomical, pun intended. So there's a lot of competition to see what actually gets funded and what goes ahead. And then if it is funded, we get to do the mission, we hopefully get the data, and then we get to run the numbers and see what new things, what new facts we can glean from that data. And so this lecture series will intersperse information about both what we know as well as how we know it. And with a bit of me describing the instrument or technique that was developed to answer some question. So I'm going to go ahead. So as an outline, the course format is going to be over 3 parts. This first part is the future and history of the sun, the history and future. And then next week, we'll be talking a bit more about the sun's radiation and space weather at Earth. So that is more my specialty in terms of heliophysics and astronomy, is that interaction and that slice of the pie right there. And then week 3 will be even more concentrated on, my exact work in the current topics in solar research. I'm going to be talking mostly about a couple missions that I'm involved with, one of which is called Sunrise, which is an acronym, like many NASA things are, and that stands for the Sun Radio Interferometer Space Experiment. And that is, I spent a lot of time working on that in my PhD and directly afterwards in Michigan. And that is going to launch 6 satellites into orbit in 2024 to observe solar activities. We'll touch on that more later. And then the other project I'll be talking about is Farside, which is a lunar array that will go on the dark side of the moon and observe a broad range of low frequency radioactivity, looking at everything from the sun to exoplanet emissions to early universe cosmology. So we'll be talking about all of that in the coming weeks. So just an outline of this session, I'm going to be answering kind of these very high level questions like, what is the sun? Where did the sun come from? What is it made of? What is its life cycle? And how do we know? So without further ado, at a glance, very high level, this is, what we thought and knew about the sun for many, many years before, the scientific revolution. It is one of the many lights in the sky. It is the brightest and warmest light that's there about half the time. And we know it follows some set pattern in the sky over the course of the year. And eventually, we figured out Earth and other planets revolve around it. And it just generally seems kind of important. Many societies worshipped the sun. It is, the major source of energy for our environment. And it is, the center of our solar system. So, so peeling back the layers a bit more, now when we talk about the sun, we say, okay, it is a star, one of many stars. It is in particular a yellow dwarf star, a G-type main sequence star that is about 4.5 billion years old, and best estimates state the age of the universe as about 13.7 or 13.8 billion years since the Big Bang. And it is made of primarily hot plasma, which is a state of matter that is essentially an ionized gas. And it produces a lot of energy every second through atomic fusion. And so what I'm going to do now is I'm going to switch over and just show the source of this image from NASA Solar Dynamics Observatory. So I'm going to stop sharing and then reshare very smoothly, hopefully. And so this is the sun today. This is as live as we can get what the sun looks like through a range of different filters, looking at a bunch of different frequencies. And so each of these gives us some new insight or new way of understanding what the sun is like. And so you can see that the sun is pretty active right now. It's not just a plain yellow disk like we sometimes think of it as. There are sunspots, there are prominences, there are lots of activity going on, and there's stuff sticking out above the surface, and there's holes in the surface. And so we're going to talk about all of this and why all this complication is there and what it all means for us. And so all of this is being basically every day recorded from space and brought down to Earth so that we can do our very best in understanding and predicting the behavior of the sun over time. And we'll learn why that's important more next week when we talk about the sun-Earth interaction. Okay, so back to the slides. Okay. So here we are. That is the sun at a very top level as of our current understanding. And so I'm going to talk a little more about, what the sun is basically made of, which is plasma. And so, like I said, plasma is essentially a hot ionized gas that, is very rare here on Earth. I mean, there are several very common plasmas. For instance, what you think of as fire is actually a plasma. That is, gas that is so hot that it's separated its positive and negative parts from the atoms into a fluid that is under the influence of both fluid interactions as well as electromagnetic forces from its positive and negative parts interacting. Lightning strikes also contain some amount of plasma. So there is plasma on Earth, but in very small quantities. But in space, that's actually what most of the matter is made up of, because the sun makes up so much mass of the solar system, and so much, the sun stars make up so much mass of the universe, that really most of the universe is plasma. And it's very chaotic, and you have to have a very large and comprehensive set of equations to actually understand and predict the dynamics of how a plasma changes. Gases are a little more nice to play with because they are usually neutral in their charge, and so they act kind of like a very free-flowing water. But once you add in the electrodynamics of it, when you split up the positive and negatives, and then they're influencing each other as they evolve, things get a bit more complicated. And so I'll leave it at that for now. So here is a star color temperature chart showing several different stars and their colors and their surface temperatures. And so you can see that there's a range going from, almost going over the whole rainbow, from, a deep red to orange to yellow, and then white and blue. And so you can also see that, they kind of evolve where the stronger colors, or the colors that are further up on the rainbow, have a higher surface temperature. And that's no mistake, really, because one of the big things that we've figured out in physics is the Blackbody Equation. And that basically tells us, in a vacuum, the surface temperature of an object will emit light in a very predictable spectrum. And so, the sun's surface temperature is about 6,000 Kelvin. Kelvin is just another way of measuring temperature, like Celsius or Fahrenheit degrees. And there's ways to convert between them. And so here you see the blackbody curves, where the y-axis here going up and down is the brightness, and the x-axis shows what colors of light or what frequencies of light we're dealing with. And so on the left, you have the blackbody curve for the sun, and on the right, you have the blackbody curve for the Earth. So the Earth, of course, is much cooler than the sun, and so it emits a much different spectrum of light, mostly much lower frequencies that we'll see that interact with our atmosphere a bit differently. And so there is this very strong tie and bond between, what color something seems on its surface and how hot it is on its surface or its interior. And so here is a brief look at what we call the main sequence stars. There are a bit more details here that I'm not going to talk about all of them, but you can see that the G class right here in the middle is yellow and very closely matches what our sun is doing in terms of both, radius, how large it is, mass, how much it weighs, luminosity, how bright it is, and how long its lifetime is. as well as how abundant it is in our galaxy from all these astronomical observations. And so there's, also on top of these main sequence stars, there's also giant stars, white dwarfs, and supergiant stars. And, starting out, if we just have some telescopes, and some basic equipment to measure the color and temperature of each star, that's all we can kind of do is just kind of keep track of how much of each star seems to be present or obviously there in our galaxy. And from there, it's kind of a puzzle. It's like, okay, how can we turn this data into a story of the life cycle of a star? And so that is what this very famous diagram attempts to do. This is called a Hertzsprung-Russell diagram. It's very famous in astronomy, and it's commonly just called an HR plot. And so you can see that 90% of all observed stars are in this main sequence that is going down in this diagonal line here. And so again, the axes here on the X horizontal axis is the spectral class, which is exactly these, colors that we saw before. And they correspond closely to the surface temperature. And so, the lower surface temperatures are more red, and the highest surface temperatures correspond to white or blue surfaces. And so you can see, there's 90% of them are along this line, the main sequence. And then there's a couple different subpopulations that we can see as well, like the red giants here and the supergiants up above in the upper right, and then the white dwarfs in the lower left. Oh, and I forgot to mention that the luminosity, or the brightness, or how much light we detect from it, is on the y-axis. And so in order to make this plot, you have to do lots of normalizing and collecting of data. To meaningfully compare these stars, you have to know how far away they are, so you can normalize the brightness, because a star that is twice as far away as another star will seem dimmer because it is further. So you have to understand and map its trajectory throughout the sky using advanced techniques that we won't get into, in order to see how far away it is, on top of the color and surface temperature that we can detect. And so just to give you a bit of intuition as to how to understand this plot, here is a plot of a typical sampling of human beings, from all ages and all sizes, and that you are plotting the weight on the x-axis, the horizontal axis, and a person's height on the y or vertical axis. And so you can see that there seems to be a main sequence similar to the stars, where if someone weighs more, typically they are taller. For instance, children are very short and they don't weigh as much as adults. But as one grows up, they get taller and they also gain weight. And then, of course, there are like outliers where there's very overweight or underweight people that are off this main sequence. But, just if knowing nothing else, looking at a plot like this, it seems to be a good rule of thumb that height is related to weight. And so going back to here, now we can try to craft a story of what this is telling us. How does when a star is born, how does it age, or how does it move along this curve? So it seems, obvious now that the surface temperature and the luminosity of the sun are very related. But how are they related? And so here is another version of this chart, with now the spectral class and the surface color worked in. And we can see that obviously brighter stars have higher energy colors, or higher frequency light. And we can also see that, just looking at the data, mass and luminosity have an observed power law of L equals m to the 2.5. And power laws show up everywhere in physics and astronomy. Oftentimes they're first observed empirically, just looking at data, and you can see how one thing varies as you change another thing. So, and then they often are great stepping off points, for trying to build up actual mathematical and physical theories for why this relationship is. And so this is a great stepping stone to trying to understand, how does something like this evolve over time? And so we also know that temperature must also be a function of luminosity. And some other empirical relationships that we've seen and also finally worked out with theory is that the luminosity scales with the radius of a star squared and also its temperature to the fourth power. So we have all these pieces as to how different variables affect other variables in terms of a star's behavior and appearance. And so from this, we worked out some basic life cycles where, a low to average mass star like our sun, a yellow dwarf, starts out with some amount of material, and that gives rise to its current size and surface temperature. And then over time, it will descend down this energy level. Over time, it will lose mass as it gives off energy, and then change its surface temperature to something cooler and become more red in color or change colors. And then finally, it will end up as a white dwarf, which are here in the lower left of this plot. And then a larger mass star will start somewhere higher up on this main sequence, but then still kind of fall down as it ages, losing mass and energy to become a lower spectral class and have less luminosity. And then eventually it will, become a red giant. And then if there's enough material in the star, it can actually go supernova and then leave behind a neutron star, which can also be a pulsar. If you don't know what pulsars are, that's fine. We won't get into it right now, really. And then for very, very large mass stars, they start the furthest up here on the main sequence and then can become red giants or supergiants. And then when they go supernova, there's so much leftover material that it collapses back in on itself and can create a black hole. So just a different kind of visualization of this life cycle is shown here, where you can start out with a nebula, which is essentially just a cloud of material that then forms into a red giant. I'm sorry. The planetary nebula and the star-forming nebula can become a protostar, which then becomes a sun-like star, and then after aging, it loses so much of its mass that the gravitational pull on the surface is not strong enough to keep it at its current size, so it actually grows. And then when it goes supernova, it can leave behind another planetary nebula and, at the center, leave behind a white dwarf. And then for the massive stars, they become a red supergiant and then can go supernova and leave behind either a neutron or a black hole. And then here is an even more detailed chart of that, where it kind of just traces out every possible path of a star's life, going from clouds of material to clustering into a protostar. And then depending on the mass of the star, it will evolve through the main sequence and then potentially have a leftover after the end of its life. And so, that kind of answers the basic question of the star's life cycle. But, what are they made of? We know it's plasma, but really, what are the dynamics of the plasma? What's the structure of the sun? It's not, continuous all the way through. It's not just a single uniform ball of plasma. So I'm trying to find a spot out of the sun. Okay, that's a bit better. Okay, so zooming in on this figure from NASA, we can see that, like one would expect, the sun has a core, and the core is where all of the fusion is happening generating the energy that gets passed up through the star and eventually out into the solar system. And so just outside of the core is something called the radiative zone, where energy that's produced in the core has to first pass through this zone in order to get up through the surface. And the radiative zone, it actually takes over 100,000 years for energy that is created at the core to work its way through this very thick layer to make it past that radiative zone. And then after the radiative zone are the convection zone. And that's where you have finally hot plasma that is, heating up and cooling down. And similar to our Earth, where there are the tectonic plates that can cause earthquakes and that, evolve over time to spread out the continents and move everything on the surface around, that is also a form of convection, but happening at a much slower pace. In the sun, the convection cells, there's lots of little mini cycles going up and down, taking hot plasma up, and then it's cooling off and then coming back down. And, part of that hot plasma is the magnetic field that's associated and generated by all of the positively and negatively charged ions that make up from the molecules of the sun. And then finally, you have the surface of the sun where, the sun ends. But that's not all. The sun has, features on its surface like sunspots that show where higher density magnetic fields are made. And that can lead to large space weather events, as we'll discuss next week. And then the sun also has an atmosphere, which we call the corona, that gives off some glow that you can see during the rare solar eclipses. When the moon totally blocks out just the main part of the sun, you can see the glow of what's around it. And we'll be talking more about that as well. Some other parts of the sun on this chart are the chronosphere. So the sun has the surface, which we call the photosphere, and that is, technically where it ends. But slightly above that is the chronosphere, and that is a thin layer above the surface where the magnetic field is still very dominant in that region and somewhat dictates how the material in that region evolves. And so that's why you can see all this fine detail, all these little light and dark spots is where, there's magnetic fields peaking up above the surface and having plasma, run around on those magnetic tracks. And then there's also streamers where there are, long outward flowing streams of plasma, sometimes from coronal holes or sunspots, and sometimes just from the greater magnetic field structure. And so here's another quick cutaway look at that peeling of the onion of the sun. So, the core at the middle, the radiative zone as the energy moves out, the convective zone where it finally turns into circulating plasma that kind of builds up different magnetic field structures. And then finally the photosphere, the surface, and then the chromosphere directly above it. And then all these other things that can happen, like the sunspots that happen on the surface, and then the prominences, which we'll talk about more next week. But those briefly are the start of a space weather event that is made from a buildup of magnetic energy on the surface that suddenly it becomes too much and explodes outwards. And then also the solar wind, which is a constant stream of ions and hot plasma coming out at a relatively not so dense level, but it is constantly coming out and is a one way that the sun is constantly losing mass is because of this solar wind that comes out and affects us all the way at Earth. So here is another cutaway description of this structure, where now you can see how large each component is. So one solar radius is the distance from the middle of the sun to what we call the surface of the sun, or the photosphere. And that solar radius is about 700,000 kilometers, or 432,000 miles. That's about 10 times as wide as Jupiter and 109 times as wide as Earth. And so this figure is actually from a textbook that I took a class in graduate school, and was written by Tamás Gombosi, who is a Hungarian immigrant that now teaches at Michigan and is one of the big leaders of space physics. Has a really great large group there that does really cool space weather prediction software. And so, yeah, and you can see that some of these zones are larger than others. The photosphere is actually very thin, and then the chromosphere, it dominates a bit larger region right outside of that surface, and then the corona extends outwards from there. Okay, and then just a word on what happens at the core. So I said that it's nuclear fusion that's happening at the core, and that's what generates all of the sun's energy. And so this fusion is possible because there's such a large collection of material that, the gravity that is the combined force of all that mass is so much that it's overcoming the resistive forces between the individual ions and molecules, that it's pushing them together with such force that it is actually combining them into larger molecules. And so what happens here is called hydrogen to helium fusion. So hydrogen is basically the most, it's the most simple element on the periodic table. It consists of only a proton and an electron. But when you have a plasma, those elements are separated into individual entities. So you have electrons and then basically hydrogen ions, which are just protons, free flowing amongst each other. And when the pressure between those parts is so large that it overcomes other strong nuclear forces, it can actually combine them into helium. And doing so releases a large amount of energy. And then that energy is then, convected outwards through the radiative zone, and then through the convection zones, and then spat out in the form of light, mostly. And so the sun right now is about 92% hydrogen and 8% helium. So all of it is the hydrogen and helium. But there are a small fraction of the sun that is made up of metals. And so this includes, carbon, and basically everything on the periodic table up to iron. And it is worth noting that, we don't really know we do know where those come from, but they do not come from the main fusion that is happening at the sun. So we know that there has to be something else that created those heavier elements, and that makes them present both in the sun as well as, what makes up the earth, and like how the earth was able to come into being with carbon and all these different metals. And so we'll touch on that soon. And so going back to the life cycle, a sun starts as a cloud of material that gets there somehow, and then through gravitational collapse, there starts to be some clumping up of material because of gravity. Things are attracted to each other. Things with mass are attracted to each other, and so as things start clumping up, the clumps start to clump into other clumps, and they eventually form a sphere of material. And then due to the energy and the magnetic fields, that material begins rotating, and that rotating makes things fall into a disk around the sun. And so that disk is called a protoplanetary disk. And all the debris in that disk eventually also clump up and turn into the planets that are revolving around that star. This is a very general understanding. This happens at a lot of stars, and we now know through exoplanet observations that, you know, there are roughly 100 billion galaxies observable in the universe, and each galaxy is predicted to have about 100 billion stars. And we think now that each of those stars probably has at least one planet. We don't, there's a mix of gaseous planets like Jupiter and rocky planets like Earth. Planets like Jupiter are easier to detect in exoplanet observations, so they're a bit more oversampled and overrepresented. But to our best guess, each star has probably a couple planets around it, and those being a mix of rocky and gas planets. One more notable feature about the sun that we know of, that we don't quite know the answer to yet, is something called the solar cycle. And so the solar cycle has been known about for many, many decades, and it is an 11-year cycle of solar activity. So for over the course of 11 years, the sun goes from calm to very active back to calm. And so this is a famous visualization of that aspect called the butterfly plot, first discovered by Edward Maunder in 1904. And so what this is showing you is a flattened look at the solar surface as viewed from Earth. And so just like Earth, you can define a coordinate system where the sun has an equator and the North and South Pole. And so what we're looking at here is solar latitude, going from the North Pole up top to the South Pole down bottom, and then the equator in the middle. And so what you're seeing here is the distribution of sunspots over the years. And so you can see that, at the beginning, quote unquote, of a solar cycle, you get a few sunspots near, plus and minus 30 degrees latitude. And then over the next 10 years, those sunspots converge to the equator. And as they converge to the equator, you get more and more sunspots. And those sunspots are potentially the start of very drastic space weather events, like coronal mass ejections and big explosions of material that come off from its surface. And so depending on where we are in this circle, you can see more or less space weather. And if you remember, when we looked at the Solar Dynamics Observatory website just a few minutes ago, you could see that there was lots of activity happening. You could see that there were several places where there were sunspots and what seemed like prominences or magnetic arches full of plasma connected to the sun. And that is because we are currently going into solar max, as we call it. There's solar max and solar min to denote the level of activity throughout this solar cycle. And so this is very predictable and has, been happening for probably a long, long time. But we don't exactly know why 11 years and why this structure in the sunspots over the years. This is a big outstanding question in our field, and we have inklings of why this is happening, but we don't have a concrete theory or a simulation that can recreate this effect. The best we can really say is that it has something to do with the internal magnetic fields of the sun. And we know also that along with this process is a flipping of the magnetic solar field. So, at the beginning of the cycle in solar min, there is a nice clean structure to the sun's magnetic field. It has a very same dipole structure that we have here on Earth, where there is a clear North Pole and a clear South Pole, and that is where most of the energy is flowing from A to B, from south to north. But then as solar maximum progresses and you get more and more sunspots, the structure of that magnetic field becomes more and more chaotic, and the disorder brings rise to these sunspots and these space weather events. And eventually the things get so chaotic and the magnetic field actually flips. So what was north is now south, and what is south is now north. And there's actually some evidence in like the Earth's crust and different observations of very old core samples that this magnetic flippening happens at Earth as well. It just takes much, much longer. And so we think it has something to do with how the magnetic field of the core of a planet or a sun or a star interacts with the rest of the body, and somehow that leads to this magnetic field flipping back and forth over time. And so, this is a problem in geophysics as well as heliophysics. And so there's been a lot of effort going into, understanding how this effect comes to be from, the structure of a magnetic core and a planet's or star's magnetic field. Very interesting, but very puzzling as well.
Alex, we had one question come in related to the solar cycle. Can you tell us where we are in the current cycle, or is that cycle something that's easily defined in that 11 years?
Yes, it's very, very clear where we are. We are going into solar max right now. I think the peak of solar max will be in a year or two. So for the next few years, we will have heightened activity at the sun and more space weather events. And so what's interesting is that, as it's happening, there's lots of activity from scientists to understand, like, okay, now we're in solar minimum, and we're doing our best to really predict when the max is going to start ramping up. And so there's a very predictive element to this as well, where we want to understand ahead of time how intense a given solar cycle is going to be, because there is some variation, as you can kind of see in this plot. Like the last, I guess the 1960 solar max was particularly maxifying. And so there's lots of work that's currently being done to understand individual solar cycles as well, and try to predict the level of activity that we're going to see.
Thank you.
Yep. Okay. And so now I'm going to talk a little bit about, where did the sun come from? We mentioned that in this typical life cycle of a star, there starts out some cloud of material that eventually condenses and ignites into a star, and then a protoplanetary early solar system can form around that. But really, where did all that stuff come from? And so, I'm going to spend the next couple slides kind of tracing our way through this very dense figure of the universe through time, tracing, starting at the Big Bang to our best knowledge, talking through the first galaxies that formed, and then eventually getting to our solar system and then the future. So starting out, Big Bang happened, roughly 13.7 billion years ago. There's still lots of open questions about this, like what is the distribution of dark matter, dark energy, and regular matter in that distribution, and then how did that affect the evolution of everything since? And so I'm not going to go too much into like inflation and all that, but there is eventually you get the first stars and galaxies form. Everything starts out as a singularity, and then spreads out into a growing infinity of space and time. And then from all that material that was, once a singularity and then more or less evenly spread out, as things spread out more, gravity starts to clump up all that matter and stuff with mass into the first stars. And so, the first stars were made of purely hydrogen. And then they did some of the fusion to create helium, but there were no minor ions or metals in the first stars because, we start out very simply just with plasma and very basic particles. And then when large stars go supernova at the end of their lives, that can give rise to scenarios where denser and larger elements are created. And so we really needed that first round of stars to seed the universe with heavier particles so that planets could start to evolve and minor ions and metals could start to be in other stars, and that would potentially change their behavior. And so, that the first galaxies and stars happened, a few hundred million years after this Big Bang, after nuclei and atoms and everything started to come to being. A few billion years down the road, you get still inflation, the expansion of the universe that we can kind of track using something called standard candles, which are a class of star that we believe to be very common and to have a sort of reference brightness. And so by tracking the apparent brightness of those stars over time, we can see how quickly they are moving away from us, because we think that, over a small amount of time, their luminosity, their brightness is constant. But if they are moving away from us, they start to appear dimmer. And so by keeping track of all of these common stars and seeing how their brightness evolves over time, we got an idea of how the universe is expanding. And now we have all these sort of secondary galaxies and secondary and tertiary stars that are made from the exploded remains of other stars that have more complex elements that have built up over time. And finally, 9 billion years in, we get our solar system, or about 4 billion years ago. And then finally, in present day, here we are at Earth. And then in the future, we expect the sun, as it spends its energy, both turning hydrogen into helium and giving off, there's the famous E equals mc squared, which is showing the equivalence between energy and mass. So it is giving off energy in the form of light primarily, but doing so must reduce its mass because of that equivalence. And so over time, both through that energy mass equivalence, as well as from solar eruptions, as well as the solar wind, which is constantly spitting off some small amount of plasma from the sun, the total amount of material in the sun is shrinking. And so the total amount of gravity that is experienced by the sun is shrinking as well. And so with less and less gravity, it actually turns out that the sun will expand over time because the material that is left is not so strongly held in towards the center by its own gravity. And so as it ages, the sun will become a more deep red because its surface temperature will decrease, but it will expand in size, but still no longer give off the same amount of energy and light. And so, in 7 or 8 or 6 billion years, that will mean the end of life on Earth due to no longer receiving a good amount of energy from the sun to sustain life as we know it. And then, of course, there's many different scenarios about the end of the universe. There's the big crunch, there's like the heat death of the universe, and then there's like a few more esoteric endings. But the one described here on this is the heat death scenario where, everything eventually spreads out. The suns eventually all become spit out all of their energy and mass, and just everything kind of spreads out so much that it is non-interactive, and the universe is eventually cold and dark, far, far, far down the line. And so in order to understand all this and try to make this understanding of our universe, we've sent out many, many satellites into space to take data. And here is just a snapshot from a NASA presentation showcasing all of those different missions, organized by what primary body that they are trying to observe. So we have lots of satellites, both revolving around Earth and that are focused on Earth, like the ISS, and lots of things that are looking down at Earth in order to understand its atmosphere, its magnetic field, etc. And then we have, lots of stuff at the moon or going to the moon, and then as well as the outer planets and Mars, as well as trying to understand our galaxy and distant galaxies. But then there are lots of things dedicated to the sun. Solar Orbiter is a big one that was just launched a few years ago by the European Space Agency. And then there's Parker Solar Probe, which is our, big flagship solar mission of the past few years. And then later we'll talk, in a couple of weeks, we'll talk about Sunrise, which is a mission that I spent a lot of time working on and still work on. And so lots of these instruments have contributed to our understanding of the evolution of the universe. Here's another view of the evolution of stars and light over time. So at the far left, you have the Big Bang, where you can see this colorful strip right here on the left is called the cosmic microwave background. And that is basically a leftover signal from the Big Bang of the very small variations in energy and temperature of what is directly after the Big Bang. And those very small variations let the process of gravitational runaway and collection actually begin, since the non-uniform parts attracted more mass, and then that could eventually lead to stars and galaxies. And so, we have a few different missions that are trying to get data on the cosmic microwave background. So there's the Planck, WMAP, and COBE, which have all sort of successively built up the detail of this cosmic microwave background that we have observed. But there is actually very little data on the structure of the universe for the first couple billion years, because there were very few stars, or sorry, not couple billion, first several tens and hundreds of millions, because there were no stars there and very little that we can point a telescope or instrument at and get data for. And so we are working on that, and that's what Farside, which I'll also talk about week 3, will try to tackle. And then finally, in our universe's history, we start to get, the first stars, and then reionization, where we get a second generation of stars, and then finally a very alive and kicking universe with lots of galaxies that evolve, and the sky becomes very active with stars. And with JWST, which you may have heard just launched this year, James Webb Space Telescope, this, along with Hubble, can look backwards from the present, because what they're doing is they're looking at both optical light as well as light that is slightly lower frequency, that is older. So by looking at this older light, it can stare back into the older parts of history, and we can try to understand this cosmic evolution a bit more. And then there's lots of ground-based radio arrays that we'll talk about as well, that contribute to this understanding of different stars and their evolution. So yeah, going back to the HR diagram, we have a pretty good understanding of why there is this main sequence. stars start out with some amount of material from their nebula or cloud of plasma that eventually compacts down into a star. So it has some starting mass that gives it some surface temperature, and that surface temperature decides what color it will be. And then as it evolves and gets older, it will give off that energy and mass in the form of light and particles, and its color will shift rightward on this plot towards green, yellow, and red, and then lose mass and lose luminosity. And then the larger stars will become giants or supergiants, and then can end in supernova that leave behind these little leftover stars like white dwarfs and neutron stars and black holes. So we have a pretty good, that's how we have come to understand the basic life cycle of a star. And, you know, it's been a long road here, and it's only possible because of so much work of lots of scientists and engineers. And so now I'm going to talk a little bit about that side of things, like how do we know? And how have we built up this mass of information and knowledge? And so it's mostly through indirect and remote sensing data. You know, we are stuck here on Earth for the most part. We cannot go up and touch the sun. We cannot scoop out a sample of the surface of the sun and then analyze it in a lab. It's far too hot. And we can't do the same for any other stars either, because they're so far away. And so all that we have really is light and other observations, like the orbits of the stars that come from their gravity. And so this is a lot like trying to understand the structure of a bell just from listening to it ring. And in this analogy, the sound is electromagnetic fluctuations, or light. And so light comprises a lot of different things that we sometimes think of as separate here on Earth. There is the optical light, which is this little strip of rainbow here in the figure here, and that is what happens to that's what comes from the sun. It's a very small sliver of that black body radiation that gets emitted, but it happens to be one strip of light that makes it through the atmosphere mostly unaffected. And so looking at this plot, you know, gamma rays, X-rays, and ultraviolet light, you know, we sometimes think of X-rays as something that we just go to in the doctor's office, but really it's just high frequency light that is so energetic that it is very prone to interacting with whatever it comes into contact with. And so it's useful in clinical settings because of that property, because it is very affected by our bone structure and the structure of our bodies in general. And so depending on how much makes it through, that can show us, you know, an X-ray of like where the bones are in our body. And for this reason, most of the gamma rays and X-rays and ultraviolet rays that are generated by the sun do not make it down to Earth because it is absorbed by the upper atmosphere. The visible light just so happens to make it through, and then all of these little peaks and valleys that you see directly to the right of it for slightly lower light wavelengths are due to different molecules in the atmosphere interacting with that particular frequency of light. And so there's, again, lots of groundwork physics that had to be laid down to understand, okay, so this element in this molecule has this many protons, this structure of electrons around it, and that makes it prone to interacting with these very specific frequencies of light, or spectral lines. And so these peaks and valleys here correspond to very common things in our atmosphere, like CO2 or water, that are very tuned to interacting with these specific frequencies. And then moving over here, the infrared spectrum is just a very lower frequency light that happens to be absorbed by many of the gases in our solar system, and then re-given off as heat And so when you have an infrared lamp, it's, giving off light in such a way that it is absorbed by the air around you, and that air then re-radiates it and goes into a higher energy state and becomes warmer. And then working our way rightwards on this diagram, radio waves are very low frequency, and they make it through to the bottom of the atmosphere at the surface of the Earth unscathed. And so this is another window where we might not be able to see it with our eyes, but we can build mechanical eyes that can sample this very useful spectrum of range of the light spectrum that makes it through unscathed, and we can answer a lot of questions from it. And then finally, on the rightmost side of it, the very, very long wavelength radio waves are blocked. And those are blocked. We'll talk about this more in the coming weeks, but the Earth's atmosphere actually has a layer of plasma called the ionosphere, and that interacts with the lowest frequency of light and absorbs it. So we can't really see below 10 megahertz. So the very, very, very low frequency waves, you have to go above Earth into space to observe. And so touching on this, this is all indirect remote sensing data, light that comes from a faraway source that we can measure and then characterize and try to answer questions with. And light is just one of the 4 fundamental forces that we know of in physics that we think describes most of the behavior out there. One of these fundamental forces is gravity, which we can kind of see also indirectly by looking at how stars orbit around each other. And then, of course, there's light, which we just spent a lot of time dissecting. And then there's also 2 other forces called the nuclear strong force and the nuclear weak force. And these are more important in atomic and subatomic interactions. And we can only really learn about them through experiments with large particle colliders. So like the LHC and all the other super colliders are trying to understand these forces. And that's what like the standard model of physics is built up on. And that is very in-depth stuff that we will not be talking too much about. But I will show this hopefully intuition building plot where it orders the fundamental forces from strong to weak. And so the strongest is the strong nuclear force. It holds nuclei of atoms and molecules together. It's very strong, but it has a very small range. So it doesn't affect intermolecular force at all. It's all within one molecule or one atom. And so next up is electromagnetic. This is not as strong as the strong nuclear force, but still pretty strong. And it has the added benefit of, being visible and propagating outwards basically forever. Then up next is the weak interaction. And this is where, not my area really, but it is dealt with in nuclear decay, where, some very complicated molecules give off subatomic particles like neutrinos and turn into slightly lighter elements. And then finally, the weakest force by far is gravity. But like light, its range is infinite. And so it's a very useful way of looking at things from far away and trying to understand what they're made of, or at least how massive they are. And so trying to combine this picture of electromagnetism and Earth, as well as the Blackbody curves from earlier, where on the left, the upper panel is the sun on the left and the Earth on the right. And so the sun is giving off all of this energy that most of which the higher frequencies are absorbed, like we said. Some visible light makes it through. And, because it's the highest frequency light that makes it through to the surface, it makes sense that everyone would want to use that in order to see things and orient themselves to the environment. And then you can see on the left here all of these different molecules that contribute to spectral absorption, of particular bands of light. So that is why that is absorbed before it gets to the ground. And then finally, the infrared spectrum is where, all or most of that spectrum is absorbed by most of the molecules altogether. And so this interaction really is the main component in the energy budget of the Earth. You have energy coming in from solar radiation. Much of it is absorbed in the atmosphere. Some of it is absorbed by the surface of the Earth. Some is reflected off. And then that whatever energy is absorbed by the Earth is then re-emitted at the Earth's black body temperature, which is about 255 degrees Kelvin, or, some 50 degrees Fahrenheit. And then, so that energy is given off in a similar sort of black body curve here on the right with the 255 Kelvin. And then some of that is then reabsorbed by our atmosphere and spat back down. And so that is actually the source of the greenhouse effect, because the CO2 and other greenhouse gases love to absorb emission of infrared, as well as those particular spectral lines that we talked about. And so that is why what is re-emitted, what we absorb from the sun's energy and then re-emit, can be stuck going between our atmosphere and our surface due to these higher levels of greenhouse gases. And then, of course, some of the heat is radiated into space from the top of the atmosphere, that which makes it through to the other side. And then one other point I'd like to talk about is that light can be polarized. And so, you often hear about polarized lenses in the form of sunglasses. And this is a mechanism that only allows a certain polarization of light through the lens. And that's why things are darker on the other side, is because you're only getting a small fraction of all the light that's out there. And so you can have light be polarized in a number of different ways. You can have a pure linearly polarized, where it's just going up and down along one single axis. You can have circularly polarized waves, where they're kind of going around in two axes, which can also be thought of as a superposition of both linear polarizations. And then elliptical, which is the most general case, where it's linearly polarized along both axes, but more so with more intensity along one of them. And so on the right, you can see kind of the shape that this traces out over time. And you can derive certain things from how light is polarized, because a lot of light is unpolarized. And that's just where you have all of these different orientations together equally. But if there's one particular orientation that is dominating, we call it polarized. And only a few things can create polarized emission in such a way. So that is often a marker for some important physical process that is happening. And so, yeah, just talking a bit more about how we know and how we've built up this knowledge of the evolution of the universe, I'm going to talk a bit more about low frequency waves, because that is where some of the most important markers for space weather come from, because we're going to be talking about that the next couple of weeks, as well as, it being my own work, I know it pretty well. So here is a summary plot of trying all of our integrated efforts of trying to catalog all the low frequency waves that we can see around us. And so zooming in, first off, the Y vertical axis is how bright it appears from Earth. So the brightest things are the easiest to detect. The dimmest things are the hardest to detect. And then the X horizontal axis is frequency, or you can think of it as the color of the light. Most of this is in the low radio frequencies, so it doesn't have a color to which that we can actually experience, but it is analogous to it. So zooming in to the very brightest things, at the very top, you have a solar type 3 burst. And this dashed line going down at around 10 megahertz delineates on the right, what we can see from the ground, and on the left, what we cannot see from the ground because of what I mentioned earlier, Earth's ionosphere actually interacting with and absorbing the very, very lowest radio waves. And so you have to go up into space to observe these, which we'll be talking about in the coming weeks. But among these low frequency radio waves, the loudest or the most intense are solar type 3 bursts. And there's also solar type 2 bursts that happen as well somewhere here on the plot. And then I'm going to point out a couple more things, and then we will look at examples of these emissions. So you can also see the sky background is very bright at this whole range of frequencies. And then there are bursts from Jupiter, as well as static emission coming from Jupiter. And then on the right here, you can see some individual things in the sky. Cassiopeia A is a supernova remnant that is very loud across the whole frequency range, including down below 10 megahertz, but we just do not have very many measurements there, so we haven't characterized it quite as well down there. And then there's also Cygnus A, which is a very close by galaxy that has these large lobes that emit very loudly in the radio frequencies. And so some examples of both of these are shown here. This is for solar type 2 and type 3 radio bursts. We'll be talking more about these in the coming weeks. Sunrise in particular is a mission formulated to better understand these types of emissions, but they are linked very closely with space weather events, including these large coronal mass ejections where the sun is spitting off large amounts of material. On the right here is what we call a coronagraph, and that is where you're basically making an artificial, solar eclipse at all times by just having a satellite that has a little piece that blocks out the middle of the sun so it can better observe the light and material that's coming in from around it. And so this white circle in the middle on the right is the size of the sun. And so the size of these structures that it can give off can be absolutely massive and can really affect things here at Earth, both, affecting our power grids as well as affecting our communications and GPS for the most intense events. So there's really a lot of time and money that's been invested into trying to understand and predict these, because now that we live in a electronically connected world, these can affect us more than ever before. And then there's also the type 3 radio bursts, which are also very bright and are affected with another type of space weather event called just a solar flare. And so here is an example of the sky background. So this is a model image of what the galaxy and the whole sky looks like at 10 megahertz. And so the most notable things you can see on here, this is a projection, by the way, so you're seeing all 360 degrees and all 180 degrees latitude. So this is a projection of seeing the whole kind of celestial sphere all around us. And you can see the most dominating thing here is the galactic curve. So this is from our Milky Way galaxy. That's the middle of the galaxy there, that white spot in the lower right. And the green strip that makes its way around is the projection of the galactic plane onto the sky. And so that is very dominant for these lower frequencies and has to be taken into account when you want to observe other things happening. There are also like the very bright single source things like Cygnus A and Cassiopeia A that we mentioned that are labeled here but are very small. So here are some zoomed in pictures of those really bright radio sources. This is Cygnus A, which is actually just this galaxy, which is that little dot on the rightmost figure in the middle of the two great big lobes. And then on the left is a zoomed in artistic rendition of the galaxy with the two fountains of plasma that it's spitting out from its north and south poles. And so we sometimes call these structures dragons, which it stands for double radio source associated with a galactic nucleus. And so this is by far the brightest dragon in our sky. And the two main lobes here are coming from fountains of plasma that are being given off by the north and south poles of the galactic core. And you can think of these like a fountain where, you know, if you have a pipe that's spitting up water, it will be contained to a column for a while, but as soon as it loses enough of its upward momentum and energy, gravity then starts to act on it, and then it will spread out into a larger structure. And that's kind of what's happening here. But instead of gravity, it is the force and energy of the plasma as it interacts with the interstellar and intergalactic medium. So at some point, the energy from this plasma fountain is equalized by the pressure of the medium that it's coming into contact with. And at that point, it's kind of splitting off from the fountain pole or the pipe and coming into this large structure. Very cool stuff. And then another bright thing that I mentioned is Cassiopeia A, and this is a supernova remnant from a relatively nearby star explosion. And again, a supernova is one of the possible end-of-life events for a large star that can often leave behind in its core a black hole or a neutron star. And so this large explosion sends out lots of debris, energy, and electromagnetic waves that go from the X-rays, optical light, and all the way down to radio waves. So this Cas A, as it's often referred to as, is a really bright marker in the sky at almost every frequency that we can look at. And so looking down a bit more at the dimmer things in this low radio spectrum, you have more, individual sources like Virgo A and Jupiter. Uranus and Neptune also give off radio waves, or are thought to, at lower levels than Jupiter. And then these two bold lines here are Jupiter if it was larger, and also coming from very far away, 10 parsecs. And so this is meant to be indicative of how sensitive a measurement we would need in order to sense a radio emission coming from an exoplanet. And so as we formulate our future missions to potentially look for exoplanets in this way, we have to scale it and make sure that it can sense this strong of a signal. Okay. And then so here are just some examples of some weaker emission, like planetary emission. And sometimes to best understand and map this out, you have to subtract out the constant sky model of the galactic plane, as well as the individual very strong sources. And so that's very much a data processing technique where, you have your data, and then you have what you think would be the data from just these very powerful things. And then so you subtract off what you know is there and in what strength, and the residual, what's left behind, can contain these weaker sources of emission that then you can look at in more detail. And so Jupiter has a few different types of low frequency emission. It has on the left here synchrotron emission. This is kind of its static emission that it's always giving off due to the interaction of plasma that is orbiting Jupiter and interacting with its very strong magnetic field. Fun fact, Earth also has this synchrotron emission, but it will be at far, far lower a frequency and far, far lower an intensity because of our less strong magnetic field. And then some other types of emission that Jupiter has are seen on the right. These are the transient emissions that are driven by different dynamics. the most powerful of which is controlled by Io, which is one of its moons that has lots of volcanoes. And so those volcanoes are constantly giving off smoke and plasma that are incorporated into kind of a ring-like structure around Jupiter that gives off emission in somewhat predictable increments because we know the period of Io's orbit around Jupiter. We can kind of predict when the next Io-controlled burst will happen. And then there's also low-frequency emission happening at Earth at all times in the form of AKR or aurora, and then different low-frequency processes associated with that aurora. So here you have it's called a spectrogram showing the intensity of radio frequency emission over time. So time is the x-axis, y is the frequency axis, so higher frequencies down to lower frequencies. And you can see both solar emission, Jupiter's emission, and then also some auroral kilometric radiation from our own Earth's magnetic field, or AKR. And then on the bottom, you can see the amount of polarization in that signature. And so you can see that the AKR is very highly polarized. In particular, it's circularly polarized that we can see by analyzing the very specific nature of the light coming from it. And then, yeah, here's just another example of different radioactivity observed in Earth. And so we're getting here to the end, and I'm just about out of time. So I'm going to kind of speed through the last few slides here to leave a few minutes for questions at the end here. But very generally, to record this data, you start out with some sort of electromagnetic wave that gets focused or received by an antenna, and optionally you can have a dish that improves the collecting area and makes more waves go into a focal point where your receiver is, and then you analyze the characteristics of the waves coming in, and then from that you can understand the color, the frequency, the intensity of the light over time. And so, yeah, here's a nice little movie showing how a wave coming in makes a voltage appear on a antenna, where you have an antenna made out of a highly conductible material. And then that voltage difference is then measured and recorded. And so by looking at the voltage difference on your antenna, you can infer the strength of the electric field that's coming into it. I'm going to skip over this part, but there's lots of ways of talking about that in terms of units. You can talk about it in terms of voltage, current, power, and resistance, and ways of going between them. You can look at the whole sky. And so this is just showcasing, there's a three-dimensional analog to degrees, which tell you like how much of a slice of pizza is, for instance, and you can think of that as a degree or a radians. And then sterradians is basically the same thing applied to a sphere. So you can tell how much of a sky or how much of a sphere you are sampling in your collecting area by putting in terms of sterradians. And then there's also different effects that we have to take into account when we're recording this data, like the projection effect on antenna sensitivity. So for instance, a linear antenna would be most sensitive to things coming in directly perpendicular to it, because the ups and downs of the electromagnetic wave would impart the most voltage on that orientation of the antenna. But as you get waves coming in from closer and closer to its north and south pole, it will impart very little voltage difference on the antenna's north-south direction. And so in order to take this into account, we have to understand the characteristics of our antenna very well. And so here's a plot of a typical dipole antenna in the rainbow colors compared to what we call an isotropic or equally receiving antenna in green. And so this showcases that effect where an antenna is more sensitive to waves coming in from a particular direction than it is in others. And then if you design very complicated antennas, you have to do very intense simulations of each of those components and understand how they interact with the electromagnetic spectrum to understand its response function. And then you can actually calibrate your antenna to the galactic brightness of the galactic background, since that is very well known and characterized at this point. And then I just have some stuff on the structure of NASA that I will skip over for now, and I will cover it again in week 2 or 3 instead. So that is the sun in a nutshell, and come back next week for this more on the sun's radiation and space weather at Earth, and then week 3 on my topics of solar research. So thanks so much for joining me today, and I'd gladly take any more questions at this point. Thank you.
Thank you very much, Alex. We appreciate your time and dedication to us and sharing this information. Just a couple questions that we received while you were presenting. The first is, can you describe an exoplanet? What is that specifically? It's kind of an understanding that it's anything outside of our solar system, correct?
That's right. An exoplanet is, so a planet is any large body that orbits a star that is not itself a star. And so an exoplanet is just a planet that's revolving around any star that's not our sun. And so, for a long, long time, we could only theorize about, are there planets around other stars? But as the state of the art has advanced, we've come up with different ways to sense whether or not a star has an exoplanet around it. And so with more and more sophisticated techniques coming online, we've found that most stars have planets of some sort.
Wonderful. And this might be something that you're going to be addressing in the coming weeks here, because you talked about solar weather, but does any of that help us understand our climate crisis and current solutions to that crisis here on Earth?
Not so much. We've had space weather affecting us for Earth's entire history. And I'll talk about this next week, but there's like a particularly famous event in the 1800s where there was a massive space weather event, and it like shut down the global telegram network, and set fire to some telegrams, and you could see aurora as far south as Hawaii. And so things have been happening like that for all of human history. But it's only now that we have a highly built up electronic society that such things are now truly, threatening or dangerous to life as we know it. I would say that, no, that the space weather we experience is relatively untethered from the climate of Earth. And like I mentioned, the energy budget of Earth is such that, we take in a lot of energy from the sun's light, but now that we've altered the chemistry and composition of our atmosphere, that energy that we're taking in can now get kind of trapped in a feedback loop because of that greenhouse gas interaction. And so the space that's just more about like the energy budget of the Earth, like that is relatively constant coming from the sun, or slightly altering over the solar cycle. I would say that the large scale climate crisis that we are facing does not have too much to do with space weather.
Thank you. Seeing I don't have any additional questions in the chat window, but if you'd like, you're welcome to come off mute and share a question that you might have for Alex, or a comment from some of his presentation today. This will be the last call for that. I see David Black came off mute. David, do you have a question you'd like to share or a comment?
Oh, I just want to say this is great. That your level of knowledge, but making it reasonably followable by us cloth heads, has really been wonderful.
Sorry, David, you broke up a little bit there, but I believe your comments of praise to Alex were heard. So thank you for sharing that. Any other questions or comments before we close today? Well, seeing none, I will just pass things off to Gordon and echo my thanks to our presenter, Alex Hegedus, for joining us. Gordon, if you'd like to close out our session today, we'd appreciate it. Thank you.
Well, I'll just say thank you to Alex and all the participants, and we'll see you next week.
Thanks all. See you then.
Thank you.
Thank you. Take care, everyone. Happy Thanksgiving. Have a wonderful time with your family. We'll see you next week. Bye, Beverly. Bye, John. Bye, Steve. Bye, Alex. Take care.
Bye.